Hello, today we are going to learn about work, energy, and power. We will start with work. Work is the external force applied on an object that causes a transfer of energy. External in this case simply meaning outside of our defined system. So, if our system were just this ball per se, gravity would be working on it. Some people define energy as the ability to do work, but you'll hear more about that later. Remember, since work is caused by a force, if something is moving at a constant rate and not accelerating, then no work is being done. This also means that if the force is perpendicular to motion, there is no work being done. In the colloquial sense of the word, this man is working incredibly hard to lift this car and run with it. But since he is applying force upwards to lift and moving forwards, as defined in physics, he is in fact not working at all. The equation for work is force times distance, like the man with the block. However, due to friction or some other force, the net force on the block is zero and it is not accelerating. So, this means that no work is being done by the man. In the video, however, I am pushing the chair across the floor. I am also applying force over a distance, and you multiply that to get the work. The greater the force or the distance, the greater the work being done. Now this brings us to power. Power is simply defined as work over time, so the amount of work done within a specific amount of time. As I just mentioned, power, P, is equal to work over time. Who has more power, me or Eli? Though we are both lifting the same object over eventually the same distance, I accelerate faster, which lowers the time. This means that overall, more work is done by me. Who is more powerful among these men? Trick question. They are both moving at a constant speed, and therefore they are both powerless because they are not doing work and are therefore have no power.
Hi, today I will be talking about kinetic and potential energy. Kinetic energy is the energy of motion, and to represent it, it is mostly mass times velocity squared and halved. Some examples of kinetic energy can be running or riding a bike. Next, we'll talk about potential energy. Now, when you think of potential energy, you want to think about something that has the potential to do energy, like batteries. It's stored energy, essentially. And the equation for potential energy is mass times gravity times height, mgh. And examples of this can be a battery or a heating pack. Now, to get more complex, there's another type of potential energy called spring potential energy. It is the potential energy specific to springs. And as you may guess, an example is, of course, a spring. In this video, we'll see how kinetic and potential energy applies in real life. Now, as we watch, we could see how I start to ride on the bike, and as I begin, I start with a ton of potential energy at the top of the hill, and as I move down, I lose potential energy and I gain kinetic energy. And you will start to see that as I move on, I start to move a little bit more up again, losing my kinetic energy and gaining potential energy as I move up, making it more difficult for me to go up. Now we will learn about the work-energy theorem, which applies work into energy. It's important to know that when there's energy, there's a system, which has items that are included within the equations. Now, these systems are called open and closed systems. If exterior work can act on the items of the system, then it is an open system. If it is not able to, then it is a closed system. An example of this is including the Earth and its gravity in a system where a rocket is trying to leave the atmosphere, where the rocket is applying force towards the Earth, and the Earth is applying gravity to keep it down on the Earth. Work The work energy theorem also states that work is equal to the final kinetic energy minus the initial kinetic energy, which, as you can see, the equation there.
The last topic we have today is about the conservation of energy and also mechanical energy. But firstly, what is the conservation of energy? Well, it's the principle that states that energy in an object can neither be created or destroyed whilst in a closed system. However, it also states that energy can in fact be transferred from one form to another. Forces that easily transfer energy into various forms are known as conservative forces, while more difficult to regain forms of energy transfer are known as non-conservative forces. Let's look at an example. Let's view in simple terms the ways in which energy transfers from one way to another. At around this point in the ball's motion, it is in a state of equilibrium. Therefore, there is no kinetic energy due to negative acceleration. There is, however, the greatest value of gravitational potential energy that will ever be present in the ball due to it being at its max height. Now, at this point in the ball's motion, the ball is moving at the fastest speed possibly achievable with its given height. Assuming the point at which I catch the ball is the height of the system, which means height equals 0, the near exact moment before the ball makes contact with my catch, the height of the ball is 0. Due to this, there is no gravitational potential energy present in the system. However, the energy in the system is still present. It was transferred from gravitational potential energy into kinetic energy, and it is important to note that the sum of kinetic energy and gravitational potential energy has remained the same throughout the object's motion. As a matter of fact, this segues our talk to the point of our next topic. Mechanical energy is the sum of the total potential and kinetic energy throughout the system. So long as no exterior force interferes with the system, mechanical energy is the same throughout. As you can see in the first photo, Ronaldo's mechanical energy is completely made up of gravitational potential energy due to him being in a state of equilibrium. In our second point, during his jump, Ronaldo has mechanical energy made up of gravitational potential energy and kinetic energy, which are both equal to each other. Note that the mechanical energy has neither increased or decreased. Finally, at the instant before Ronaldo lands, his mechanical energy is made up entirely of kinetic energy. However, the point that should be taken away from all these examples is the fact that while kinetic and potential energy change based on where Ronaldo is in his jump, his mechanical energy of the system remained the same. To end this topic, let's quickly explain when conservation of energy is no longer applicable. Take this penalty kick for example. Before the ball is struck, it is in a closed system due to no exterior forces acting on it. It also has no form of mechanical energy, but conservation of energy applies. Now though, an exterior force, Messi, has now sent the ball into row Z, whilst also shattering the closed system of the ball. Although the ball is in motion and has height above the ground, it no longer conservation of energy no longer applies due to no mechanical energy being present before the kick. While it is present afterwards, energy was not conserved, and exterior energy applied would be defined as work exterior.